All right, let's take a look at this one here. So we're looking at the function r equals 2 times the sine of 3 theta. So remember, this is going to be the sine of n thetas, as long as n's a nice integer, are going to be, those graphs are always going to be flowers. And here's an odd number, so it's going to have exactly that number of petals. We looked at this graph, or at least something similar to that graph. We did it with cosine, but sine would be similar. So something like this. And then we want to know the slope of the lines at the petals. Now again, this was the cosine graph, so that's a little different, but we're going to be doing it for the sine. So we want to find the slope of the tangent line at the tips of the petals. So first, let's find our formula for the slope of the tangent line. So remember that dy dx, the slope function, will be dy d theta divided by dx d theta. And so that's what we're going to be looking for here. Dy d theta over dx d theta. And remember, we get that by parametrizing our polar equation, so we get it into parametric equations. Remember, x is r cosine theta, and y is r sine theta. So, in this example here, x would be 2 sine 3 theta times the cosine theta. And y would be 2 sine 3 theta times cosine, times sine of theta. Okay, so those are going to be our functions. And then again, we can derive, if we need to, the formula. Or in this case, I'm just going to use the fact that parametric equations, that I just need to do the derivative of that over the derivative of that. So working that out here, dy dx on top would be the derivative of y. So it's going to be 2 sine 3 theta times the derivative of sine theta. So 2 sine 3 theta times the cosine of theta. Okay, plus sine theta times the derivative of 2 sine 3 theta. Okay. So 2 sine theta, and derivative of sine 3 theta would be cosine 3 theta times the derivative of 3 theta. Okay, and on the bottom, I'm going to have the derivative of x. That'll be 2 sine theta, or 2 sine of 3 theta times the derivative of cosine, which would be minus sine theta, plus cosine theta times that derivative as well. So 2 cosine theta times derivative of sine, which would be cosine of 3 theta, times 3. And then just do a little bit of housekeeping here. I'm going to have 2 sine 3 theta cosine theta plus 6 sine theta cosine 3 theta. And then all that is going to be divided by a minus 2 sine 3 theta sine theta plus 6 cosine theta, cosine theta cosine 3 theta. Okay, so that's my derivative. All right, and now I want to evaluate it at the tips of my rose petals. The tips of my rose petals. A couple ways to get to this idea of tips of my rose petals. I remember when we were graphing these, the tips of the rose petals happened at the high or low points of the XY version of the graph. So we can come up with these by saying to ourselves, when is this equation here, y equals 2 sine 3 theta, when does it reach its high and low points, right? And where do they occur at? Because that's where we're going to need to evaluate. That's where we're going to need to evaluate. Okay? Or we can go in and use a little bit of technology and plot the graph. So I'm going to explain it to you the by hand way, and then I'll also explain it to you graphically. I'm going to start with the graph version first. So my function was r equals 2 sine of 3 theta. Okay. And again, to graph these, you can see it actually finishes, because Desmos will tell you this, at pi. So I'm going to put in my little parameter a, add a slider in for a, set a between 0 and pi, with an increment of, I typically use pi over 12. Okay. That way I can go in pi over 12, that's 15 degrees. So there we are, 15 degrees. We reach our high point at 30 degrees, or pi over 6. You can keep going. There we are, 45, pi over 3. Keep going, 75. Actually, here we are at 90, which is pi over 2. 115, 120, 135, 150, or in radians, that would be 5 pi over 6. We hit our last thing, 165, and then finishes up at 180 at pi. So the three places we need are this right again. Three places we need are at pi over 6, pi over 2, and 5 pi over 6. But we could also get those by hand by just saying all those places are when the radius was 2. In other words, we could solve the equation here, 2 sine 3 theta equals 2, or alternatively, when is sine of 3 theta equal to 1. That would happen when 3 theta is equal to, well, the first time around, pi over 2. And we go around the second time to 5 pi over 2. I got that right. Sine is 1 at just pi over 2. And then the second time around, 5 pi over 2. And then third time around. Oh, also we allow for minus 1. That's the one I was missing. We also allow for minus 1, which would be at 3 pi over 2. I missed that one. Because it can be either plus or minus, because, again, minus would allow it to also be at its high point. And then there's actually 3 more between 0 and 6 pi, but since our graph only needs to go to pi, we actually only go around 1.5 times, so this is enough. And then you solve those by dividing by 3. And that's how we get our pi over 6, pi over 2, and 5 pi over 6. Okay, so those are the places where we need to evaluate this dx or dy dx. Okay, so we go ahead and do that on our calculator. This is where calculator is really nice. Of course, you can do a lot of this stuff somewhat in your head as well. Dy dx, First evaluate it at theta equals pi over 6. So if we put pi over 6 or 30 degrees in here, here's some things that are going to happen. If you were going through here, sine of 3 times pi over 6, sine of 3 times pi over 6 be sine of pi over 2, which is 1. So we're going to have 2 times the sine of pi over 2, which is 1, times the cosine of pi over 6, which is square root of 3 over 2. So in the end, you just get square root of 3. Over here, you have 6, sine of pi over 6, which is 1/2, cosine of 3 times pi over 6, which is going to be cosine of pi over 2, which is 0. So that whole term just disappears, and so we're left on top of the square root of 3. On the bottom, again, that's going to be 1. Sine of pi over 6 is 1/2 times the minus 2. Leaves us with a minus 1 so far. Cosine of 3 times pi over 6 is going to also once again be 0. The whole thing goes away. So we end up with just square root of 3 over minus 1, or a slope of minus square root of 3. Okay. And we then likewise would evaluate at theta equals 5 pi over 6. And what you're going to find is if you do that, you're going to get square root of 3. And likewise, we would evaluate at pi over 2. And what's going to happen when you do pi over 2 is cosine of pi over 2 is 0, so that whole term goes away, 0. Cosine of 3 pi over 2 is also 0, so that whole thing goes away. On top it's 0. Cosine is again 0. And in the bottom, this is going to be a bunch of 1s. This is going to be a bunch of 1s, so with a minus 2, but there's a 0 on top. And so that one has a slope of 0. So if we go back to the graph here, at our first tip, it has a slope of negative square root of 3 at that tip, positive square root of 3 at that tip, and a flat horizontal tangent line of 0 at that tip. And that's what we found here using our formula.